Record the computer. Let's review midterm 2. Okay. For today's goal, first, we just review chapter 2 about IIT system. Okay. Actually, before I talk about IIT system, do you remember what we talked about in chapter 1? What do we talk about? Like what's the main things? Yeah, firstly, just tell me what's the name for chapter 1. Yeah, actually, the name for chapter 1 is signals and systems. Yeah, so which means we just talk about firstly signals and then systems. Signals, what's that? Do you know? Do you remember?
Signals is what goes into the system.
Huh?
Like info.
Yeah, it is input like signals and output also is signals. Yeah. And the signals usually like it is a thing can represent some physics quantities. Yeah, do you remember? Yeah, for example, the sound signals, the voice signals, the video signals, the temperature signals, and other pressure signals. Am I right? Yeah, these signals actually it can represent a physical quantities in the real world like that. Am I right? This is signal. What system?
Gathers the input, takes an output.
Yeah, that's right. The system is just like we have input and we have output, and we just deal with something to the input and get the specific output. Am I right? The relationship between usually like if I just write this down, the action it is what it is signal. Am I right? Yeah, usually we use this to represent input signal. So when xn or xt. Yeah, yn or yt. Actually, yn xt is signal, am I right? The yn yt also a signal, am I right? But then if I just represent it, this is system. Yeah, the system is the relationship between the input and output, am I right? Yeah, it's just a deal with something for the input and got the output. Yeah, and similar for the continuous one. Yeah. Okay. And then for in the chapter 1, we learn what is signals, what is system, am I right? And we also learn some different types for signals, am I right? We learn like class 1, like energy signal, the class 2 power signal, and the class 3 like the otherwise signals, am I right? And also we learn some like different like how to transform signal like shift, scale, and inverse like that. Yeah. And then we learn systems, and then we learn some properties for signals. Am I right? Memoryless. Yeah, do you remember inverse? If this system is inverse and like stable, choral, and linear or time invariant. Yeah, this is system's property. Am I right? And then, like let's summarize. Like in the chapter 1, we just learn some basic thing for systems and signals and system. Yes, some basic thing. Am I right? And in the chapter 2, what do we learn?
To turn off the convolution.
Yeah, convolution.
Like what the response is the output.
Yeah. What's the name for chapter 2? Yeah, actually the chapter's name is LIT systems. Yeah, so like we learn some properties for systems like memoryless, linear, or the LIT system. What does that mean? Why we call this system LIT system? Sorry, LTI system. Why we call this system LTI system? What does the LTI system mean? What does the LTI mean? L, what does that mean? Linear.
Linear,
Time invariant. Yeah, LIT system, which means this system is linear and time invariant.
Yeah.
That makes sense to you? Yeah. So what does that mean? Which means in chapter 2, we focus on a special system. Yeah, this special system is which is linear and time invariant. Yeah, when we talk about the LIT system's property, we talk about the stability and the chirality, right? But we didn't talk about linear and time invariant because they are already linear and time invariant. We just based on this thing, based on the system is linear and time invariant. And then for what you have already talked about the convolution thing and the we learn convolution sum, we learn convolution integral. It's just based on this system is LIT system. If this system is not LIT system, you cannot use convolution sum or convolution integral. Yeah, just remember that. Okay, the LIT system we learn in this chapter. Okay, and for the we learn linear convolution. I'm right. Yeah. Actually, so you didn't take the deep learning class, am I right? You haven't taken a deep learning method, am I right? Yeah, actually, why here is linear convolution? Because the convolution is a linear operation. Yeah, that's the reason why the LIT system can use it is a linear operation. What is linear operation? Do you know? Huh? Yeah, the linear is just a similar what we talk about the in the beginning. The linear is just like if you like a multiple choose multiple constant to the input, and then you can get the same constant to the output like that. Yeah, and if you have this bx1 2 t, you can get the a y1t plus b y2t like that. Yeah, actually the convolution has a similar property. Okay, and then we learn something about impulse response. What is impulse response? Yeah, HNHT. Yeah, but what is exactly is? Yeah, yeah. Yeah. Actually, you talk about some properties for the impulse response, some calculation, some computation. But just remember, the impulse response is what? It's just the output. It is firstly it is an output, right? OT. We call it this is impulse response. Actually, it's output, right? What is this output? This output is just like a signal goes through a system, right? And the input signal is specific signal, delta T or delta N. Am I right? Yeah, so what does that mean? For the impulse response, the input is fixed, delta T or delta N. But the Hn and Ht will be different because the system is different. We have different system, and the output obviously will have different output. Am I right? That makes sense to you? Yeah, just remember that. Yeah, the impulse response is just the output. When the input is delta N or delta T, what's the name for delta N and delta T? You know? Impulse. Yeah, impulse function. Yeah, and just remember, actually, these two function is very important. What is delta T? Delta T is this one. Here, am I right? What is delta N? It's just a that makes sense to you? Yeah, just remember this one. Okay, and for the linear convolution, yeah, we have some analytical approach. Do you remember we sum that the convolution sum and the convolution integral, and then we have some geographic graphical approach. Actually, do you know what is graphical approach? Yeah, we talk about the, huh?
We have one, other graph. Output graph.
Yeah. Yeah, you're right. Like, you know, for the analytical approach, we just give you two slides, and those slides, one is for convolution sum, one is for convolution integral. The graphical approach, actually, I didn't sum that, give you a summary, but do you remember when we talk about some example, and I just like draw xt or xn, right? I give you some figure, and also I give you the figure for ht, and then convolution, which means it's just like do a multiple and add. Yeah, do you remember we talk about some examples? Yeah, so like for some for the graphical approach, usually the convolution sum, like the discrete term, like convolution like signals will be more use this method. Yeah, like yeah, and sometimes you can see if you have some like signals, and these signals for the n, xn, and it will have like this one, this one, this one, this one, and the hn, it will has the hn, have this one, this one, this one, this one, and it is easy for you to convolution like multiple them and add them together using the figure. That makes sense to you? Yeah. Okay, and the input, yeah, for the analytical approach, we can use some properties. What properties? The shifting,
Distributed.
yeah, distributive, yeah, commutative, and the other one is associative.
Associated.
Yeah, just like you try to make it simple, yeah. And for the impulse response, yeah, we just if we want to like tell this the LID system is correl or not correl, stable or not stable, do we need to care the input signal? Yeah, if we want to tell LIT system is correl or not correl, stable or not stable, what we will see? What we will, how can we do tell? Minus? Yeah, past like a present. But do you remember what we talked about when you want to tell the LIT system is correl or not correl? You just see the impulse response. If the impulse response involves the negative part, do you remember that? And for the stability, you just check the sum for the impulse response. It is infinite or finite. Yeah, do you remember that? So which means if we want to tell a LIT system is correl or not correl, stable or not stable, we don't need to care the input signals. We just check the impulse response. That makes sense to you? Yeah, we can from the impulse response to tell if it's correl or not correl, stable or not stable. Yeah, we can judge, we can tell if it is the correlity and the stability. Am I right? Yeah, okay, this is what we learned for chapter 2. And okay, before we continue, let's talk about one very important thing, the time domain system representation. Do you know what does that mean? Time domain system, what does that mean? Which means this system will change according to the time. Am I right? Yeah, because the domain is time. Am I right? Yeah, actually, why we talk about this content here? Have you ever heard the other domain system or signals? Yeah, actually, there is time domain. Do you know what is time domain mean? Yeah. And which means my system. Yeah, which means my system will change based on the time. Which means the x as will t, am I right? Oh, n is also time, am I right? And then my signal or my system will change, like based on this is input, and then it will change, or change. The axis always time, am I right? Yeah, but we have the other domain. I think you heard about this, but you just don't know what is it, like a frequency domain. Yeah, which those are very important to different like domain system. Yeah, we will. Why we talk about time domain here? Because we want to talk about the frequency domain in next chapter. Yeah, and then let's when you understand the time domain system, and then it will be easier for you to understand the frequency domain. Yeah, we know like the time domain system is just the relationship between input and output, am I right? The time domain system, which means you have the relationship between the input and output, and the variables is time, am I right? Yeah, this is like an example for the time domain system, am I right? Also, this one, yeah, you can have different form for the system, and this one, and this one, and this one, always they are all time domain system, am I right? Because the variable is time. Okay, let me ask you a question. What is the impulse response for this system? Do you know? Yeah, it's just like, huh? Yeah. I think you are right. It's just like this. Yeah, like a 2 delta n, because you can see your, yeah, I think you know that. Yeah, the 1 equal xn convolution with hn, am I right? Yeah, and hn, yeah, also hn convolution with the xn is the same thing, am I right? So which means you're like if you this is the output for now, it is xn negative xn minus 1 plus xn minus 2, and which means like if your hn equal that one, you just use what property? Distributive, yeah, and shifting, yeah, shifting property, yeah. Okay, let's talk about the impulse response. Actually, like I talk about everything we talk about in chapter 2, it's just related to our IT system. If your system is other different system, and you cannot use what we talk about in chapter 2. Yeah, the impulse response, the convolution sum, the convolution integral, yeah, you cannot use it. Yeah. And actually, we talk about why we want to focus on LIT system in the beginning of chapter 2. Yeah, because you can see the most many systems in the real world can be modeled as a LIT system. Yeah, and also the LIT system is easier for us to analyze. Yeah, okay. And this is impulse response example, and this is the other one. And okay, let me ask you, what is the input-output relationship for if your impulse response is this one? I think this is firstly, what's the input? What's the output? What's the equation for the output? Yeah. Yeah, the xn convolution with hn, am I right? Yeah, you can hn or convolution with xn. Yeah, for now you have hn, and then using shifting property, distributive property, shifting property, you can easily get the output. Am I right? Yeah, this is here. That's I just want to tell you contain the time domain system, because the system and the signals will change based on the time. Yeah. Okay. Yeah, this is prepared for the next chapter. Okay, let's review the convolution sum. What is a convolution sum? Yeah, it's just like this one. Yeah, I'm right. Yeah, the convolution sum is just like the output can be represented as a convolution sum. Yeah, and for the convolution sum, actually, it can be. We want to find the relationship between the input and output. We use the convolution sum, but we want to like you give me the input, you give me the input signal, you give me the input response. I want to convolution with those two and get a beautiful representation for the output, am I right? Yeah, we don't like the complicated. So the convolution sum usually can be computed analytically, especially when both the input and the input response are given. Yeah, and actually, do you remember for the convolution sum, how can we calculate it? Do you remember?
I mean,
Like for the convolution sum, how can we how many ways, how many cases we will have like do you remember? Yeah, two cases. The first one is just the xn and the hn are given as short input sequences. All right, then you can use some shift properties, those four different properties to simplify the equation. Am I right? And the second one is when the xn and hn are defined with a closed form, the key is to convert the convolution sum into the geometric series sum as this one. Also, or this one, or this one. Those are two different situations. This situation is just like your range is from n naught to positive infinity. Then you use this equation. If you're like a range for time is from n naught to n1, the specific range, and you need to use this equation. Alright. Yeah. So when you prepare a cheat sheet, and the midterm review is very important for you, so you better to put and for this one, I think it is easy. I think those two have the similar questions. If you have two upper bounder, what should you do? If you have two upper bounder or two lower bounder, what should you do?
so
Yeah, you need to discuss the situation, am I right?
yeah.
Yeah, if you have two upper bounder, which means you need to decide which one you need to use. If like because for the upper bounder you need to choose the lower one, am I right? For the lower bounder you need to choose like a bigger one. So you need to discuss that. Yeah. We have some examples for them. You need to review it. Any questions so far? Okay. Let's talk about the convolution integral. Actually, the convolution sum and the convolution integral is very similar, but the convolution sum is for the discrete time system, RIT system, and the convolution integral is for the like a continuous time CT RIT system. Yeah, and also if you wanted to compute it analytically, when both the input xt and the input response ht are given, actually there are also two different cases. The first one is the xt and ht are given as input sequences, like simple input sequences, and then what you can do? Do you know? Yeah, you can use some properties to simplify that. And for the case 2, usually the xt and the ht will give in terms of this one. Yeah, like do you know why? Do you know why? Do you know why? Do you know why the xt and ht are given in this one? What's this? What's this? Yeah, I never talked about this before, but do you know what's this? The ut, actually we can ignore that because the ut will be removed when the t greater equal than t naught, am I right? So this atom, what is this atom? What's this one? Yeah. What's the name for this function?
The
Exponential. Yeah, it's potential function, am I right? We know like its potential function can be transferred to which function? Using Euler equation. Yeah, you can transfer it to the sinusoidal function. And we also talk about all the periodic signals can be represented as sinusoidal function. That's the reason why usually like these signals can be represented in terms of this one, because all the periodic signals can be represented in this form. Yeah, and if your STHE are given in terms of this one, and then usually you will have this equation. Yeah, and then you will use this one to resolve to get the final result. That makes sense to you? Yeah. Any questions so far? Okay, and then, yeah, the key here is to remove the unit step function ut minus t now by changing the bounds of integration to make the integration computable. Yeah, if let me ask you a question. If you want to remove u here, what you should do? Or what you can do if you want to remove this item? Switch what?
Down.
Yeah, switch the bounds. Yeah, usually like the when this bound should be from negative infinity to the positive infinity, right? Yeah, but this one, if you remove this one, which means your t should be greater equal than t naught, am I right? Otherwise it will be zero. You don't need to put it here. So just remember the like the delta function, impulse function, impulse function, and the unit function is very important. Yeah. Okay. Let's try to review some examples, problems. Yeah. And this is our input signals, and this is our response, like impulse response. And the question is let you to compute the convolution yn. We know yn equal like yn equal xn convolution with hn, and then we just like try to use the function step by step. I'm right. Yeah. You know like this convolution can be represented as this form. I'm right. Okay. Let me ask you a question. What kind of question you will use this equation? What kind of question you don't need to use this equation? You know? Huh? Yeah, actually for DT signal, you also can, you also, sometimes you also don't need to use this equation. Yeah, just back to here. If your xn and hn are given as short impulse response, you don't need to use this equation to get your final result. But here you can observe your like input signals and impulse response. It's not like a simple like short impulse sequences. I'm not. So you have to use these equations, and then just remember that. Yeah. Then you have xk, you have xn hn. Then you can have xk and hn minus k. I'm right. So you can have this one. Okay. What's the next step? Huh? Yeah. Here, actually, you speak the point. Yeah, find the bounds. I'm right. Actually, why you want to find the bounds? Because you want to remove the unit step function. Yeah. Okay. Let's review it one by one. For this one, what is your key? If you want to remove this one, what your key should be? Yeah, greater equal than 4. So your bound will become this one. For me, let me. I'm right. Yeah, it will be 4 to positive infinity. Okay, why I can like put 4n here? Like I have
We put it out.
huh? Yeah, why I can took like 4 power n out? But why this negative like 1/2 cannot take it out? Yeah, that's right. You observe that. You can see this is key. Like this 4 over n and 4, actually it's just a bit breakdown. Am right? And you, because this part is the key will change. Am right? So you cannot now put the item related to n related to key out, but you can put the item related to n out. That makes sense to you? Okay, then what's the next step? Yeah, the other boundary, am right? For this one, am right? So how can we find what equation we can use here? Yeah, 2 minus n plus p greater or equal than 0, am I right? And then we can find the p bound. Yeah. This is just like combine those two. Combine those two. Those two can be combined together. For this one. And then we have this one. We need to, and from here we have this one, k greater or equal than n minus 2, am I right? And this is the lower boundary, am I right? Actually, we have the other lower boundary, 4. So for now, we need to decide which lower boundary we need to use, am I right? So we need to talk about n minus 2 and 4, which one is bigger, which one is smaller, am I right? When n minus 2 greater or equal than 4, and it is n greater or equal than 6, which will be the lower boundary? Are you sure?
And greater than
Actually, you can see the k should greater or equal than n minus 2, am I right? So here we want to decide the lower boundary, which means we need to decide the k is n minus 2 or 4. And actually, you are right. Yeah, for this situation, the lower boundary should be n minus 2 because n minus 2 is a bigger one. Am I right? Yeah. So n minus 2 should be the bigger one. It should be the lower boundary. And then you have this equation. And for different situation, if n minus 2 is smaller than 4, which means 4 is a bigger one, which means 4 should be the lower boundary. Yeah, we have this equation. And then you can you can continue to calculate using the equation here. Am I right? Yeah, but I didn't calculate it, but you can continue. Yeah. Okay, any question? Okay, that's great. Okay, let's talk about the other example. Yeah, this is our input signal. And if I want this signal convolution with those two, what should we do? What? Switch? Yeah, just remember, it's not a multiplication, it's a convolution. So if you see this question, you just use the properties firstly, all right? What properties you can use? And firstly, you need to use the distributive, all right? Try to remove the possible convolution delta t minus 1 minus xt convolution with the delta t minus 1. Yeah, you get this one, all right? That makes sense to you? Distributive. All right? Huh? Any question? Okay, and then what property we use? Huh? Commutative? Convolution property, yeah, which one? Convolution property will have 4. We just use distributive, right? And what for this step, what property we will use? Huh? Yeah. Yeah, let us review the property. Here, the property is a shifting property, commutative, distributive, associative property. And for this one, do you think what property, like for this step, what property we will use? Shifting? Yeah, it's shifting. You can see. Okay. Yeah. Then you can see, you can use the shifting property to get this equation. I'm right. And if you have this equation, actually you can easily get the whole. I'm right. Yeah. What is the xt minus 2? Yeah. No. What is xt plus 1? Sorry. Plus 1, which means. Yeah. It will left shift 1 unit. I'm right. What is xt minus 1? Right shift. Yeah. But it is here is a minus, which means it is a flip. Yeah. Not flip this, it flip this. Yeah. Like this, because yeah. And then you just add them together. it will like this. Am I right? That makes sense to you? Yeah. So this is the final one. So just pay attention. The conclusion is different with the multiplication. Yeah. The multiplication is just like, oh, you have this one, and then this one maybe is you just try to just get the result in this point. Am I right? But the conclusion is not. Yeah. Okay. Any question? Okay. And then let's try to review the chorality and stability of our system. Sorry. And for the chorality of variety system, how can we tell if the system is choral or not choral? We want this part, we don't want this part, am I right? Yeah, so which means this is HT, we don't want this part, we want this part, am I right? So which means if you check your HT, impulse response, if it has this part, it will not choral. That makes sense to you? Yeah. So yeah, this is just like for the stability, which we just want the sum for the like impulse response is infinite. I'm right? Yeah. So infinite or finite is finite. Yeah. So it has a limited value. So we will have this equation. You need to tell, although if your like sum for the impulse response is limited or unlimited, that makes sense to you? Okay. Oh, like for the if your DTLIT system have the similar form for the impulse response like this, and then there are some rules. For the first one, if your A absolute A smaller than 1 and B absolute B greater than 1, and then your like system is stable. Otherwise, it will be unstable. And for this CTLIT system, if your A is smaller than 0 and B greater than 0, and then your system is stable. Otherwise, it will not be stable. Sometimes, if this atom is removed, or this atom is removed, actually it's a similar thing. Am I right? So in your cheat sheet, you need to put this in your cheat sheet, and this in your cheat sheet. Am I right? Okay. And let's try to review the determine like a problem. I don't know if you finished the homework. Yeah, this is problem 2.28 and 29. Yeah, determine the chorality and stability for the following system. How about this one? Let's try to tell, is it choral or not choral? Firstly. Yeah, what?
Nothing. Future.
Yeah, which means you can say UT -2. This one is greater or equal than 0, which means your T is greater or equal than 2, right? Which means your like HT always is this part. Is the positive part. The positive part doesn't lead to the like passive signal. Yeah, okay. So stability, stable or not stable? Yeah, actually, just check. Sorry, check this one. Yeah, we have. Yeah, E negative. So A should A if smaller than 0, it will be stable. Am I right? And what is A here? Yeah, that's right. Yeah, it's choral and stable. So that's the reason why I let you to this one put your cheat sheet, because if you know this and you don't need to use this equation to calculate it. Am I right? Even you can. Yeah. Okay. Let's check. How about this one? Let's check. It is stable or not stable? Oh, it is choral or not choral? Yeah, it is choral because T greater or equal than 0, right? It just how about stable? Actually, for the stable, you cannot use this equation. Because here is a T. Am I right? Yeah, but so let's just try to use the equation. So what do you, if you want to check it is stable or not stable, you need to try to put T, like a dt. All right, you want to check this one, all right? Yeah, and do you remember, actually, this one actually is very familiar. It's familiar for us. If we want to use this one, actually, we just try to find the which derivative, the after derivative, it can get this one. So you can see, if you derivative this one, you can get this one. Yeah, derivative, if you derivative this one, you can negative t. Here, negative will remove and be negative t. All right. So which means this is, you can get this, and then, yeah, because ut, t is greater equal than 0, right? Yeah, because ut is removed, so it is 0, right? So if this one is infinite, what's the value for this one? Yeah, it is 0, right? If it is 0, what is it?
1.
Yeah, it's minus
1.
minus 1, right? So it will be 1, right? So it is stable or not stable? Not stable? Oh, yeah. Yeah, because it has limited value, right? So it is stable. Yeah. Yeah, you can join us. Okay, how about this one? First, let's check it is correct or not correct. Yeah, when you check it correct, you just check this part. Yeah, it's correct. So stable. It is stable or not stable? Yeah, which means we want if we want like 0 to positive infinity 2e negative t minus e t blah blah blah. This one et, right? We want this one, right? But yeah, you can see it is a kind of complication. Yeah, but you observe our t goes to positive infinity, right? So which means this value will go to positive infinity. Yeah, because t and e is like a 2-point blah blah blah, right? So this one will go to positive infinity. If there is a minus, so which means it will be goes to like negative infinity. So it is stable or not stable. If it is infinite. Yeah. Oh, sorry. I just yeah, it is not stable. Yeah, I will show the result later. Yeah, I think I just put it yeah. And how about this one? Sorry, I just show the result. I think I just put it. Yeah, you can see this one. Why it is horror? Let's talk about why. Yeah, which you can see here. We should let n minus 3 greater equal than 0, n greater equal than 1, right? So it is the correct, right? Why it is stable? Because similar with this equation. Yeah, you just add them together, you will find this one goes to 0 faster than this one, much faster than this one. Yeah. So how about this one? Why it is correct? Sorry. Why it is correct? Because n greater equal than 0, right? Why it is stable? For this one, actually, we can use the equation here. Right? A here, smaller than 1, right? So it is stable. That makes sense to you? And how about this one? Yeah. Why it is not correct? Yeah, because we should let 3 minus n greater equal than 0, right? So n should smaller equal than 3. So it will involve some value here in this area. So it is not correct. Actually, it is stable. Yeah, because you can see we can use this equation. Yeah, because for now, if there is the n here is negative, right? So we can use this here. The b should if b greater than 1, it will be stable. Here b is 5, right? Yeah, so it is stable. And yeah, this is correct, not stable. Yeah, okay. Yeah, this is what we talk about today. And there is a very important thing. Yeah, we will have similar example or similar questions in midterm 2. You can see. I give you, what's this? Sorry, wait me for a moment. Yeah, we have a XT and we have also a YT. Yeah. Yeah, this is YT. And I want you to find the impulse response. Yeah, you can see from this one, you can see you can represent the YT using XT, am I right? If you have this equation, actually you can easily get the impulse response. Am I right?
Yeah.
And then you can, based on the impulse response, to decide if it is chiral or not chiral, stable or not stable. This is chiral. Are you sure? Are you sure it is? Yeah, so it is not chiral, right? Yeah, I just asked you the question. It is not chiral, but it is stable because it's just a three values, am I right? Yeah, okay, and then since the system is not chiral, the present also involves a future input. It's just use the blah 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 to explain why the zero. Yeah, that makes sense to you. Yeah, you can review it, but we have similar questions in the midterm too, and I will give you a input and let you to represent output using the input and find the impulse response. Yeah, similar thing.
Yeah.
Yeah. Okay. Any questions so far? Okay. Yeah. Good luck for the midterm too. Yeah, we will have you can prepare a one-page thesis. Okay.